Hello, my name is Alexandro Ayala, and today I will be teaching you guys about rotational mechanics on rigid bodies. As your instructor today, I will focus on teaching you guys the basics about rigid bodies and how we can calculate the stabilities at points based on the rotational movement of the body. In order to do this, we will have to go over rigid bodies, Euler's equations of motion, stability, angular momentum, and surface energy. We will finish off the lesson with a review example revolving around the stability of a rigid body. Before we can move on and start learning about the rotational movement of a rigid body, we have to define what a rigid body is. In the simplest manner, a rigid body is an object that does not experience any change in shape, which is better known as deformation. There is still a possibility that deformation may occur in this ideal body, but it is usually small enough to be negligible. Rigid bodies are also heavily used when trying to determine the stability of an object when it undergoes motion, which may be rotational or just plain linear movement. We also tend to use these rigid bodies in aerospace, such as the image still to the right. As you can see, the plane figure seems to be under investigation through its rotational mechanics, such as the roll, the yaw, and the pitch. This can easily influence the lift that the model would produce during actual flight, which is why investigating and studying the rotational mechanics of a rigid body is important. This leads us to the rotational mechanics of a rigid body. A rigid body undergoes rotational movement when it is undergoing motion about one of its axes. This type of movement is seen in many ideal processes today, such as this example, where the Earth is rotating about the Sun. As depicted, it is an ideal process, so it is going about one of its axes, but changing direction in the other. When trying to depict this motion, it would be difficult to focus on the overall position of the object as it rotates, which is why instead of focusing on displacement, we will be focusing on the center of mass that is undergoing rotational movement. A pair of equations that just so happen to focus on this are the Euler equations of motion. Euler's equations of motion are a set of expressions that can represent the applied torque in three directions and also heavily rely on the second law of motion, which states that the force in the direction is dependent on the mass of the rigid body as well as the acceleration of the object. These equations also allow us to determine the rotation frame that the body undergoes when it rotates about one of its axes. As stated earlier, instead of focusing on the overall displacement of the object, Euler instead focuses on the fixed center of mass to calculate torque and momentum with much more ease. To understand the specifics of the Euler equation, we need to better understand the parts that make up the equation. In the inertial frame of the rigid body, our applied torque is simply the change of angular momentum over time. But since we are more focused on the rotational effect, we have to take more into account. The Euler equation down here below shows how our coordinate frame is centered around the center of mass. The space frame is dependent on the body's frame, as well as the cross product of the rotational matrix and the angular momentum. This is the general form of Euler's equation, which we can easily simplify into three expressions to the right, down here. And these three expressions show how the torque can be calculated in all three separate directions. In order to determine stability, we utilize the Euler's equation of motion with the Jacobian matrix. If we solve for the change of W over time for the directions that are not rotated about, we can then enter the derivatives of the non-rotated direction in the Jacobian matrix. With the Jacobian matrix, we can solve for the determinant and the trace. If the trace is 0 and the determinant is positive, you are at a stable point. Else, if the determinant is negative, it is unstable. And before we can talk about energy surface and angular momentum, we might want to better understand angular momentum. We know that angular momentum is a cross product between a second order tensor and a vector, in which the second order tensor is the inertia, while W, our vector, is our rotation vector. Angular momentum happens to be determined on the rotation direction as well as the inertia matrix, as we just said. And angular momentum also coincides with energy surfaces, where if the rotation is stable, both the energy and momentum will intersect at a point where both are fixed values. And as for the intersection of energy and angular momentum, the energy of surface of an energy ellipsoid and the angular momentum tend to intersect, as we said, at points where the values are fixed. And this only occurs at stable locations of the rigid body. As you can see down here, they're intersecting at specific points. And to better explain what the ellipsoid and the sphere is, the angular momentum indicates the rotational movement of the rigid body in all three of its directions, and it tends to vary at different points, while the energy surface is the product of kinetic energy at each of these points. And now that we have gone over all of these things, we will be going over an example that will talk about stability of a rigid body. So suppose that we have a rigid body that is not going under any applied torsion, and it is rotating about the x1 axis. We want to determine whether the body is stable or unstable. So since we are told that there is no applied torsion to the rigid body, we know that our Euler equations will all be set to 0 on the left-hand side. Over here, I put them on the right-hand side, but earlier they were n, which were represented of the torsion. And so applying these to the Eulers and simplifying the three expressions, we get these three expressions. And since we know that the body rotates about the x1 axis, that means our angular momentum, our rotation about x1 is 0 when it is changed over time. So we know that dw1 over dt, which is the change of rotation as time passes, is equal to 0 about the 1 axis. So we now want to determine the values of the change of the rotation value of axis 2 and the change of rotation about x3 as time passes before we can start investigating the stability of the rigid body. So if we rearrange the equations, we get these two values. And then with these two values, we have to take the derivatives in terms of the non-rotative term. So we'd have to take derivative of W2 of this equation, and the derivative of W3 of this equation, before we can insert them into Jacobian. And once we have that, we can insert them. So after taking the derivative of the expression, we get our Jacobian matrix, which just so happens to be this. As you can see, after we took the derivative of this and this, we were left with just the dependent on the rotation about axis 1. And we know that the trace is just the addition of the diagonals, summation. And since there are no other values other than 0, that means our trace is 0. And as for the determinant, we'd have to do the cross product between them. But we know that the diagonals are 0, so it'd be 0 minus the product of these two. And we can simplify them into an easier expression. Once we apply the negative to this, it just so happens to become this. And since our trace is 0, our stability depends on the determinant. Recall that earlier we said that if the determinant is positive and the trace is 0, then our rigid body is stable. Well, otherwise, if our trace was 0 and it was negative, it'd be unstable about that point. But earlier we said that we know that the inertia 1 is the smallest, while inertia 3 is the greatest. So setting these up, we can easily tell that the numerators will be positive, since I3 minus I1 will give us a positive number because of this, and I2 minus I1 will also give us a positive number. So with the determinant being this, we know that it will be positive, and since our trace is 0, we satisfy the condition that the trace is 0 and our determinant is positive, making the rigid body at this point stable. And that is all. Thank you for watching.